Today I'm presenting my internship work summary. During this internship, I worked on multiple domains including digital design, CMOS fundamental, processor architecture, communication protocol, and two major projects. Those are an AI-based timing analyzer and UART IP design. So let's understand each of them. In this slide, we are going to understand the concept of finite state machine, commonly known as FSM. A finite state machine is a mathematical model used to design sequential digital system. Unlike combinational circuits, where the output depends only on the current inputs, FSM considers both present inputs and past history. This is achieved using states. An FSM consists of finite number of states, input, outputs, and transition between these states. At any given time, the system is in one specific state, and based on the input, it transitions to another state while producing an output. Now, moving on to the Millet finite machine. A Millet FSM is a type of finite state machine where output depends on both the current state and the current input. This relation can be expressed as output equal to function of state and input. Because the output depends directly on input, the Millet machine responds to faster input changes compared to other FSM types. It also requires fewer states to implement a given functionality, making it more efficient in terms of design. However, one important point to notice that since the output is directly affected by input changes, it may change instantly when the input changes, even without a state transition. Now, let's look at the key feature of Millet machine. First, it provides an efficient design with fewer states, which reduces hardware complexity. Second, it is highly suitable for real-time application because of its fast response. Third, it generates output quickly since it does not wait for a state change. However, a limitation is that it may produce glitches in the output due to its dependency on input signal. Now let's understand the diagram shown in this slide. At the center, we have the combination logic block. This block is responsible for determining both the next state and the output based on the current input and the present state. On the left side, we see the inputs entering the combination logic. These inputs, along with the current state, are processed to generate output. On the right side, the output are produced from combinational logic block. Below, we have a memory block. This memory stores the current state of system. It receives the next state from the combinational logic and updates the present state accordingly. There is a feedback loop from the memory block to the combinational logic. This loop represents the current state being continuously fed into system for processing. So overall, this diagram clearly shows how inputs, combinational logic, and memory work together in Millet FSM to produce outputs based on both state and input. In this slide, we are looking at Verilog implementation of Millet finite state machine along with its stimulation output waveform. Let me first explain the code in detail. We start with a module declaration named Millet. The input to this module are clock, reset, and data input denoted as DIN. The output is DOUT, which is declared as register because it is assigned inside an always block. Next, we define the state encoding. Here, two registers are used, state and next state, each of two inputs. This allows us to represent up to four states. We define four state using parameter. S0 represents no match, S1 represents detection of 1, S2 represents detection of 1, 0, S3 represents detection of 1, 0, 1. So basically this FSM is designed to detect the sequence 1, 0, 1, 1. Now moving to the state register block, this block is sensitive to positive edge of the clock and reset. If reset is active, the state is initialized to S0. Otherwise, on every clock edge, the present state is updated to next state. This is how the FSM transition between states synchronizes. Next, we have combinational logic block, which determines both the next state and the output. Since this is Millet FSM, the output depends on both the current state and the input. Initial E, DOUT is set to 0. Now let's go state by state. In state S0, if the input DIN is 1, the next state becomes S1. Otherwise, it remains in S0. In state S1, if the input becomes 0, it moves to S2. If the input is 1, it stays in S1. In state S2, if input is 1, it transitions to S3. Otherwise, it goes back to S0. In state S3, if the input is 1, then the sequence 1011 is detected. So DOUT is set to 1. And the next state becomes S1 to allow overlapping sequence. If the input is 0, it moves back to S2. Finally, the default case ensures the system goes back to S0 in case of any unidentified or undefined state. Overall, this code implements a Millet sequence detector for the pattern 1011 where the output is generated immediately when the last bit of the sequence is reset. Now let's move to the waveform. In the waveform, we see four signals: clock, reset, input DIN, and output DOUT. The clock signal is continuously toggling, which drives the state transition. The reset signal is initially active to initialize the FSM to state S0 and then it becomes inactive. Now observe the input signal DIN. It is applied as sequence of binary values over time. As the input sequence progresses, the FSM transition through states internally. When the sequence 1011 appears in the input stream, the output D out goes high. You can clearly see D out becomes 1 exactly at the moment when the last one of the sequence is reset. This shows the key property of Millet machine. The output changes immediately with input without waiting for the next clock cycle. After detection, FSM continues operation, allowing overlapping sequence as well. So this waveform verified that our Millet FSM is correctly detecting the sequence and producing output at the right time. In this slide, we are going to understand the concept of more finite state machine. A more finite state machine is a type of FSM in which the output depends only on the current state of the system and not directly on the input. This can be represented as output is equal to the function of state. This means that even if the input changes, the output will not change immediately. The output changes only when the state changes, which typically happens on a clock edge. Because of this behavior, more machines are more stable and predictable compared to Millet machines. The output remains constant within a state and does not fluctuate with input variation. Now, let's look at the features of more FSM. First, it produces glitch-free output since output depends only on the state. It does not get affected by sudden input change, which eliminates unwanted fluctuations. Second, it is easier to design and debug. This separation between state and output logic makes the system more structured and simpler to analyze. Third, it requires more state compared to Millet FSM for implementing the same functionality. This is because outputs are tied only to state and not inputs. Finally, it is slightly slower response. The output changes only after the state transition, meaning it has to wait for the clock edge, unlike Millet machine which respond immediately. Now let's understand the block diagram shown in the slide. On the left side, we have the input entering the next combination logic block. This block determines what the next state should be based on the current input and present state. The output of the block is fed into the state register. The state register stores the current state and updates it on every clock pulse. This is controlled by clock signal shown below the register. From the state register, the current state is sent to the output combinational logic block. This block generates the output based only on the current state, which is key characteristic of Moore machine. This is also feedback path for the state register back to the next state logic. This loop ensures that the current state is continuously used to determine the next state. So overall, this diagram clearly shows that in Moore FSM, the output depends only on the state and all transitions are synchronized with the clock, making the system stable and reliable. Here, we are looking at Verilog implementation of Moore finite state machine along with the simulation waveform. Let me first explain the code in detail. We begin with the module declaration named Moore. The inputs are clock, reset, and data input DIN. The output is D out, declared as register since it is assigned inside an always block. Next, we define the state encoding. Here we use 3-bit register for state and next state, which allow us to represent up to 5 states. These states are defined as S0 represent no match, S1 represent detection of 1, S2 represent detection of 10, S3 represents detection of 101, S4 represents the detection of 1011, which is the final output state. So, this FSM is designed to detect the sequence 1011, similar to the previous Millet design, but implemented using Moore approach. Now moving to state register block, this block is triggered on the positive edge of the clock and reset. If reset is active, the system initializes to state S0. Otherwise, on each clock cycle, the current state is updated to the next state. This ensures synchronizes operation of FSM. Next, we have the next state logic. This is implemented using case statement based on current state. In state S0, if the input is 1, the system moves to S1, otherwise it stays in S0. In state S1, if the input becomes 0, it's transitioned to S2, otherwise it remains in S1. In state S2, if the input is 1, it moves to S3, otherwise it returns to S0. In state S3, if the input is 1, it transitions to S4, indicating that the sequence is almost detected, otherwise it goes back to S2. In state S4, the machine moves to S1 to allow overlapping sequence, meaning it can detect consecutive pattern without restarting completely. This, the default case, ensured that any undefined state is redirected to S0. Now, let's look at the output logic. Since this is Moore FSM, the output depends only on the current state. So here, if the state is S4, the output D out is set to 1. For other state, the output is 0. This clearly shows that the output is generated only after the system reaches the final state. Unlike Millet, where the output depends on both state and input. Now let's move back on to the waveform. In the waveform, we can observe the signal clock reset input DIN and output DOut. The clock signal is continuously toggling, which drives the state transition. Initially, reset is applied to bring the FSM to state S0. Now, observe the input signal DIN, which is given a sequence over time. As the input sequence progresses, the FSM moves through state S0 to S4 internally. When the complete sequence 1011 is detected, the FSM enters the state S4. At this point, the output DOut becomes 1. Unlike the Millet machine, you can notice that the output align with the clock and changes only after the state transition. This shows that Moon machine produces output only based on state, making it more stable and free from glitches. Also, after detection, the FSM continues operation and supports overlapping sequence. So this waveform confirms that Moore FSM correctly detects the sequence and generate output only when the final state is reached. In this slide, we are comparing Millet and Moore finite state machine, and then we will briefly look at NVIDIA transformer engine. First, let's discuss the Millet finite state machine. In Millet FSM, the output depends on both the current state and the input. This means that whenever the input changes, the output can change immediately without waiting for a clock edge. Because of this property, Millet machines have faster response to input change. They are also more efficient in terms of design because they require fewer states to implement a given functionalities. However, this direct dependency on input can sometimes lead to unstable output or glitches if the input changes rapidly. Now moving on to more finite state machine. In more FSM, the output depends only on current state and not directly on the input. This means that the output changes only when the state changes, typically on a clock edge. As a result, Moore machine produces more stable and predicted outputs since they are not affected by sudden input variation. However, to achieve the same functionality as Millet machine, Moore machine usually requires more state. Also, their response is slightly slower because the output update is tied to state transition. So overall, Millet machines are faster and require fewer state, while Moore machines are more stable but may need more state. Now let's move to the NVIDIA Transformer Engine. NVIDIA Transformer Engine is a performance optimized library developed by NVIDIA to accelerate the transformer-based deep learning models. It uses this FP8 precision, which is lower precision format, to significantly improve computation speed and reduce memory usage compared to traditional higher precision format. One of its key features is that it dynamically adjusts the precision during computation. This ensures that while performance is improved, the accuracy and stability of the model are maintained. It is specifically supported on NVIDIA Hopper architecture GPUs, which are designed for efficient low precision operation. Additionally, Transformer Engine is well integrated with framework like PyTorch, making it easier for developer to use it in a real-world AI applications. So, this slide highlights the key difference between Millet and Moore machine and also introduces a modern high-performance computing concept used in AI acceleration. Slide, we are moving from digital design concept to CMOS technology, which forms the foundation of modern VLSI circuits. First, let us understand what CMOS is. CMOS stands for complementary metal oxide semiconductor, and it uses combination of NMOS and PMOS transistor. These two types of transistor work in complementary manner, meaning when one is on, the other is off. This complementary operation is what makes CMOS highly efficient. Now, let's look at the key features of CMOS technology. This is first and most important is low power consumption. CMOS circuit consume power mainly during switching, which makes them highly energy efficient. Second, CMOS provide high noise immunity. This means it is less affected by unwanted electrical disturbances, ensuring reliable operation. Third, CMOS allow high density, meaning a large number of transistors can be integrated onto single chip. This is why CMOS is widely used in modern integrated circuits and processor. Now let's move on to CMOS characteristic. One of the most important characteristic is voltage transfer characteristic or VTC. This curve shows the relationship between input voltage and output voltage of CMOS inverter. There are key parameters associated with this. Vout, which is output high voltage, VOL, which is output low voltage, VIH, the minimum input voltage recognized as high, and VIL, the maximum input voltage recognized as low. These parameters helps us understand the switching behavior of the inverter. Now, looking at the performance matrix, noise margin is an important factor that determines the reliability of the circuit. Higher noise margin means better immunity to disturbance. Propagation delay determines the speed of circuit. It represents the time taken for the output to respond to change in input. Now let's understand the diagram shown here, which represents the CMOS inverter. At the top, we have CMOS P transistor connected to VDD, which acts as a pull-up network. At the bottom, we have NMOS transistor connected to ground, which acts as pull-down network. In the input signal is applied to the gates of both transistor, and the output is taken from common node between them. When the input is low, the PMOS transistor turns on and NMOS turns off, pulling the output to high. When the input is high, the NMOS turns on and PMOS turns off, pulling the output to ground. So this Inverter produce an output that is complement of the input. Now let's move on to MOSFET of operation. A MOSFET operates in three main regions. The first is cutoff region where the transistor is off and no current flows. Second is linear region where the MOSFET behaves like a transistor, allowing the current to flow in controlled manner. Third is saturation region where the MOSFET act like a current source and is used for amplification or switching purpose. There are also some important effects like channel length modulation, which reduces the effective resistance and slightly affect current flow. Body effect increases the threshold voltage of the transistor, which impacts its switching behavior. So overall, this slides explain the working of CMOS technology, inverter operation, and MOSFET behavior, which are fundamental to VLSI design. Here, we are discussing important aspects related to power optimization techniques, advanced device structure, and layout consideration in VLSI design. First, let's understand the power dissipation in CMOS circuits. Power dissipation mainly occurs in three forms. The first is dynamic power. This is power consumed during switching activity when transistor changes states from 0 to 1 or 1 to 0. It is the dominant component in most digital circuit. The second is static power. This is the power consumed when even when the circuit is not switching, mainly due to bias currents. The third is leakage power, which is caused by leakage currents flowing through transistor even when they are supposed to be off. This has become more significant in modern nanoscale technologies. Now, let's move on to optimization technique used to reduce power consumption. One important technique is voltage scaling. By reducing the supply voltage, we can significantly reduce the power consumption since power is proportional to the square of voltage. Next is clock gating. In this method, clock signal is disabled for inactive parts of circuit, preventing unnecessary switching and saving power. Another technique is power gating. Here, entire block of circuits are completely turned off when not in use, which helps reduce leakage power. Now let's look at layout effects. During physical design, parasitic elements such as unwanted resistance and capacitance are introduced. These are called parasitics, and they can affect the performance, delay, and power of the circuit. To minimize these effects, matching techniques are used. That these ensures that critical components are placed systematically and carefully, improving accuracy and reliability, especially in analog design. Now, moving to advanced technology, starting with FinFET. FinFET is a modern transistor structure that uses three-dimensional design instead of a traditional planar structure. Because of this 3D structure, it provides better control over the channel. This results in lower leakage current and higher performance, making FinFETs widely used in advanced semiconductor technologies. Finally, let's discuss the BiCMOS technology. The BiCMOS is combination of CMOS and bipolar junction transistor technology. It combines the advantages of both. CMOS provides low power consumption while BJTs offer high speed and better analog performance. Because of this combination, BiCMOS is commonly used in high speed and analog or RF circuits where both performance and efficiency are important. So overall, this slide highlights the power consideration, optimization method, layout challenges, and modern transistor technology used in VLSI design. This forms a crucial part of designing efficient and high performance circuits. We are moving into processor architecture concept, specifically pipelining and instruction execution. First, let us understand pipeline basic. In a processor, instruction execution is divided into multiple stages instead of completing everything at once. This technique is called pipelining. The standard pipeline flow consists of 5 stages. Those are instruction fetch, instruction decode, execute, memory access, and write block. These stages are commonly represented as IF, ID, EX, MEM, WB. The main advantage of pipelining is that it improves throughput. Instead of executing one instruction at a time, multiple instructions are processed simultaneously, each at different stages. So, at a given time, one instruction is being fetched, other is being decoded, other is being executed, and so on. This parallel execution significantly increases performance. Now, let us understand the data path for an add instruction. Consider an instruction add R1, R2, R3. In the IF stage, the instruction is fetched from memory. In the ID stage, the processor decodes the instruction and reads the values stored in the registers R2 and R3. In the EX stage, the ALU performs the addition operation using the values from R2 and R3. In the MEM stage, there is no memory access required for this instruction, so this stage is effectively skipped. Finally, in the WB stage, the results of the addition is written back into register R1. Now, moving on to the data path for load instruction, consider the instruction LWR1, 0, R2. In the IF stage, the instruction is fetched from memory. In the ID stage, the base register R2 is read. In the EX stage, the effective memory address is calculated by adding the offset to the base register. In the MEM stage, the data is read from the calculated memory address. Finally, in the WB stage, the fetch data is written into register R1. So, unlike the add instruction, the load instructions make use of memory stage. Now let's compare the RISC and CISC architecture. RISC stands for Reduced Instruction Set Computer. In RISC architecture, instructions have fixed length which simplifies the decoding and execution. It follows a load or store architecture, meaning only load and store instruction accesses memory, while other operation works on registers. This results in faster execution and effective pipelining. On the other hand, CISC stands for Complex Instruction Set Computer. In CISC, instructions have variable length and support multiple addressing mode. The instructions are more complex and can perform multiple operations in single instruction. However, this complexity makes execution slower compared to RISC and also make pipelining more difficult. So overall, pipelining improves performance, different instructions follow different data paths, and RISC and CISC represent two different design philosophies in processor architectures. In this slide, we are discussing processor architecture concepts, including MIPS architecture, memory organization, and system architecture. Now, let us understand the MIPS architecture. This is a type of RISC architecture which is designed for simplicity and high performance. It uses a fixed instruction format which makes instruction decoding easier and faster. There are three main types of instructions. The first is R-type instruction, which are used for register-to-register operations such as addition and subtraction. The second type is I-type instruction, which include immediate values are stored and used for operations like loading data or conditional branching. The third is J-type instructions, which are used for jump operation to change the flow of execution. Because of its fixed instruction format and simple design, this is highly optimized for pipelined execution, making it efficient and fast. Now, let's move on to system architecture. First, the one human architecture. In this architecture, a single memory and the single bus are used for both instructions and data. This means that instructions and data cannot be accessed simultaneously. As a result, this creates limitation known as one human bottleneck, which can reduce the performance. The next is hardware architecture. In hardware architecture, separate memory units and separate buses are used for instruction and data. This allows simultaneous access to both instructions and data, enabling parallel processing and resulting in higher performance compared to one human architecture. Now, let us understand the memory architecture. Memory in computer system is organized into a hierarchical manner based on speed, cost, and capacity. At the top, we have register, which are faster and most expensive but have very small storage capacity. Next is cache memory, typically implemented using SRAM, which is very fast and used to store frequently accessed data. Below that is the DRAM, which acts as a main memory. It is slower than cache but has larger capacity. Finally, we have storage devices like SSDs and hardware, which are slowest but provides very large storage at the low cost. Now let us understand the diagram shown here. The diagram represents the memory architecture in pyramidal structure. At the top of the pyramid, we have CPU, registers, and cache memory. These are extremely fast but have very limited capacity and are expensive. As we move downwards, we reach main memory, which is RAM. It offers a balance between speed, cost, and capacity. Further down, we have a solid state memory such as SSDs, which are non-volatile and provide moderate speed and storage. At the bottom, we have a virtual memory and mechanical hardware drives, which are the slowest but offers very large capacity at low cost. So as we move from top to bottom, speed decreases, cost per bit decreases, and storage capacity increases. This hierarchical design ensures efficient performance by keeping frequent used data in faster memory. In this slide, we are going to understand the fundamentals of FPGA and SOC, which are widely used in modern digital system design. Let's start with FPGA basics. FPGA stands for Field Programmable Gate Array. It is reconfigurable hardware device, meaning it can be programmed even after manufacturing. Unlike fixed hardware like a SAC, FPGA allows designer to implement and modify digital logic circuit multiple times. This makes them highly flexible and suitable for development and testing. Now, let's look at the architecture of FPGA. An FPGA mainly consists of configurable logic block, also called CLBs. These blocks contain lookup tables and flip-flops, which are used to implement logic functions. Next, we have interconnect network. This is programmable routing structure that connects different logic blocks together. Then there are inputs output blocks, which acts as interface between the FPGA and external devices. Finally, we have block RAM, which provides on-chip memory for storing data during operation. Now let's move on to the features of FPGA. FPGA supports highly parallel processing, meaning multiple operations can be performed simultaneously. They are reprogrammed, which allow flexibility in design and debugging. They are very useful for prototyping, especially before finalizing hardware design. However, compared to ASIC, FPGA are slower and consumes more power. Now let's look at the application of FPGA. FPGA are used in 5G signal processing, AI acceleration, radar system, and also in aerospace and defense application, where flexibility and performance are important. Now, let's move on to the SoC, which stands for System on Chip. And SoC integrates an entire system onto single chip. This includes processor, memory, and various peripherals, all combined into one compact design. This integration reduces size, power consumption, and cost, making SoC ideal for modern electronic devices. Now, let's look at the main blocks of an SoC. The first block in the CPU, which can be based on architecture like ARM or RISC-V. Next is memory, which includes cache, SRAM, DRAM for strong instruction and data. Then we have the bus systems such as AMBA, which enables communication between different components. Finally, there are peripherals like UART, SPI, and I2C, which allows the system to interact with external devices. Now, let us understand the features and uses of SoC. SoCs are the software programmable, meaning their functionality can be controlled using software. However, their hardware architecture is fixed once designed. They provide good balance between performance and cost, making them efficient for large-scale production. Now, looking at applications, SoCs are widely used in smartphones, IoT devices, automotive system, and industrial automation, where compact designs are efficiency and are essential. Overall, the slides explains how FPGAs provide flexibility and reconfigurability, while SoC provide integration and efficiency in system design. In this slide, we are going to understand ASIC fundamentals and compare FPGA, SoC, and ASIC technologies along with their architectures. First, let's start with ASIC basics. ASIC stands for Application Specific Integrated Circuit. As the name suggests, it is designed for specific application or task. Unlike FPGA, which is reconfigurable, ASIC is fixed once it is manufactured. This means it cannot be modified later, but it is highly optimized for its intended function. Now, let's look at the feature of ASIC. ASIC provide the highest performance among all the hardware implementation because they are custom designed for particular application. They also consume the lowest power, making them highly efficient. However, they are not reprogrammable, which means any design change requires redesign and refabrication. Additionally, ASIC development involves a high initial cost due to design complexity and fabrication processes. Now, let's understand the ASIC design flow. First step is RTL design, where the system is described using hardware description language like Verilog. Next is the synthesis, where the RTL code is converted into gate level representation. Then comes placement, where components are arranged physically on the chip. After that, routing is performed to connect all components using metal interconnections. Finally, the design goes for fabrication, where actual chip is manufactured. Now, let's compare FPGA, SoC, and ASIC. FPGA offers high flexibility and allows fast development because it can be reprogrammed multiple times. SoC provides a balanced solution by integrating different components on single chip, offering a good mixture of performance and cost. ASIC provides the highest performance and lowest power consumption but lacks flexibility. Now, looking at the time to market, FPGA has the highest time to market since it does not require fabrication. SoC has the moderate development time, and ASIC has the lowest time to market because of its complex design and manufacturing process. Now, let us understand the FPGA architecture diagram. In this diagram, we can see multiple configurable logic blocks, each containing LUTs and flip-flops arranged in a grid structure. These blocks are connected through programmable interconnects, which allows flexible routing between components. We also have input-output blocks on the edges, which connects the FPGA to external devices. Additionally, block RAM is included for on-chip memory. Overall, this structure allows the FPGA to be reconfigured to implement different digital circuits. Now let's move on to SoC architecture diagram. At the center, we have AMBA bus, which connects all the components of the system. On one side, we have CPU cores, which can be ARM or RISC-V based. Connected to it is the memory system, including cache, SRAM, and DRAM controllers. We also have peripherals such as UART, SPI, and I2C, which enables communication with external devices. Additionally, components like DMA, timer, and GPIO are included for system control. There may also be optional GPU or accelerator for enhanced performance. All these components are integrated into single chip, making SOC highly efficient and compact. So overall, this slide highlights the ASIC fundamentals and compares different hardware platforms and explains the FPGA and SOC architecture in detail. In this slide, we are going to understand the AMBA protocol and its bus architecture, which is widely used for communication inside system on chip design. First, let us start with the introduction to AMBA. AMBA stands for Advanced Microcontroller Bus Architecture. It is a standard developed by ARM to define how different components inside a chip communicate with each other. AMBA is widely used on soft designs to ensure as efficient and organized data transfer between processor, memory, and peripheral. Now, let us understand the purpose of AMBA. The main goal of AMBA is to standardize on-chip communication instead of designing custom communication protocol for every system. AMBA provides a common framework. It also improves performance and scalability, allowing designers to easily integrate multiple components and expand the system when needed. Now let's move on to AMBA bus architecture. AMBA follows a hierarchical bus structure. This means different types of bus are used for different performance requirements. There are mainly two categories of buses. AXI and AHB are high performance buses used for high speed data transfer. AB, ABP is a lower power bus used for connecting simple peripherals like UART timer and GPIO. Now, why we need this hierarchy? The reason is to separate high speed and low speed operation. High performance components like processor and memory uses AXI or AHB, while low speed peripherals uses APB. This separation reduces the complexity and also help in minimizing power consumption. Now let's look at AHB, which stands for Advanced High Performance Bus. AHB uses single shared bus architecture where multiple components share the same communication path. It supports pipeline operation, which improves throughput by allowing overlapping of operation. It also supports bus transfer, meaning multiple data transfer can happen in a sequence without interruption. AHB uses centralized arbitration to decide which component gets access to the bus at a given time. Now, where is this AHB used? AHB is typically used for connecting high-speed components like processor and memory controller. Now, let's move on to AXI, which stands for Advanced Extensible Interface. AXI is a high-performance protocol designed for advanced systems. One of its key features is that it has separate channels for read and write operation, allowing parallel data transfer. It supports multiple outstanding transactions and even allow out-of-order execution, which improves overall system performance. Now let's look at the 5 channels in AXI. The first is the write address channel, abbreviated as AW. Next is the write data channel as W. Then we have write response channel as B. For reading, we have the read address channel AR. And finally, the read data channel R. These separate channels enable AXI to achieve high throughput and efficient communication. So overall, AMBA provides a standardized and efficient communication system with AHB and AXI handling high performance tasks and APB handling low power operation. We are continuing with the AMBA protocols, focusing on APB, AXI variants, and how these buses are integrated within a SOC. Firstly, let's understand APB, which stands for Advanced Peripheral Bus. APB is low power and simple bus designed specifically for connecting low speed peripherals. Unlike AHB and AXI, APB does not use pipelining, which keeps its design simple and reduce power consumption. It operates using two-phase transfer mechanism consisting of a setup phase and an enable phase. Because of its simplicity, APB is not suitable for high-speed data transfer, but it is very efficient for peripheral communication. Now, looking at where APB is used, APB is commonly used for peripherals such as UART, SPI, and I2C. It also used for components like GPIO and timer, which do not require high-speed communication. Let us move on to AXI4 versus AXI4 LAN. AXI4 is high-performance version of AXI protocol. It supports bus transfer, meaning multiple data transactions can occur in a sequence, which improves efficiency. Because of this, AXI4 is typically used for high-speed components such as memory and DMA. On the other hand, AXI4 Lite is a simplified version of AXI. It does not support the bus transfer, which makes it less complex. It is mainly used for control register and configuration interface, where simplicity is more important than speed. Now, let's understand SOC integration using AMBA. In a typical SOC design, different buses are used for different components. The CPU communicates with the memory using AXI, ensuring high-speed data transfer. DMA also uses AXI to efficiently move large amount of data. Peripherals like UART and timer are connected using APB since they require low power and simpler communication. This combination combination of buses allows the system to achieve both performance and efficiency. Finally, let's conclude this topic. AMBA plays a crucial role in ensuring efficient communication within a chip on system on chip. AXI provide high performance for data-intensive operation, while APB provides simplicity and lower power for peripheral communication. Together, they form a balanced and scalable architecture which is essential for modern software design. In this slide, I will explain the project, which is an AI-based timing analyzer designed to automate the timing analysis in digital circuit. First, let's understand what the AI timing analyzer is. This is a Python-based tool developed to analyze the timing report generated during VLSI design. In digital circuit, timing analysis is a crucial step to ensure that the signal propagates within the required time constraint. Traditionally, engineers manually inspect timing report to identify the violation, which is time-consuming and error-prone. This tool automates this entire process. It reads timing report automatically, identifies the timing violation, especially negative slack, and provides intelligent suggestion using AI-based logic. The key formula used in this analysis is stack equals required time minus arrival time. If the slack is negative, it indicates the timing violation, meaning the signal is arriving later than expected, which can lead to incorrect circuit operation. Now, let's understand the working of the tool. The tool takes timing report as input. This report typically contains detailed information about the signal paths, delays, and timing constraint. A parser model processes this report and extracts important parameters such as start point, which indicates where the signal originates, endpoint, where the signal is captured, and slack value, which determines the timing correctness. Once the data is extracted, the analyzer module evaluates the slack value and identifies any violation. After detecting violation, the tool generates a summary report that highlights critical path and problematic areas in the design. Now, let's look at the model overview. The project is divided into multiple Python models for better organization and scalability. The parser.py module is responsible for reading the timing report and extracting relevant data. The analyzer.py module processes this data and identifies negative slack value, which represents the timing violation. The AI helper.py module provides intelligent suggestion to fix this violation based on predefined logic and analysis. Finally, the CLI.py module presents the output to the user in clear and readable format through the command line interface. This modular design makes the tool easy to maintain, extend, and integrates into larger design workflow. Now, let's understand the AI-based analysis feature, which is the core strength of this project. The tool classifies the timing violation based on severity. If the slack is less than minus 0.3, it is considered a severe violation. In such cases, the tool suggests the technique like inserting pipeline stage or breaking complex logic into smaller parts to reduce delay. If the slack is less than 0 but not highly negative, it is considered a moderate violation. In this case, this tool suggests reducing fan out or optimizing logic to improve timing. These suggestions mimic real-world VLSI optimization technique, making the tool practically useful. So overall, this project automates timing analysis, reduces manual effort, and provides intelligent recommendation, making it highly valuable for modern digital design workflow. This demonstrates the integration of VLSI concept with AI-based automation. On this slide, I'm presenting the second project, which is design and complete SIC implementation of UART IP block. Let me start by explaining the UART IP design. UART stands for Universal Asynchronous Receiver Transmitter. It is a fundamental communication protocol used for serial data transmission between devices without requiring a shared clock signal. In this project, we have designed a fully functional UART IP core which can be integrated into larger systems such as SOC for communication with external peripherals like sensor, microcontroller, or computer. This design includes both transmitter and receiver model handling serial to serial and parallel to serial data conversion along with control logic for the start bit, stop bit, and data framing. What makes this project significant is that it is not limited to simulation. It has implemented a complete ASIC flow, taking the design from RTL all the way to GDSII, which represents a fabrication ready layout. For this implementation, we have used Sky130 process design kit, which provides real semiconductor technology libraries and rules. This has used OpenLane and OpenROAD, which are industrial relevant open source tools to perform the entire physical design flow. Now, let me walk through the ASIC flow in detail. The process begins with RTL design and simulation, where the UI functionality is described using Verilog. At this stage, functional correctness is verified through test bench. Next comes synthesis, where the RTL code is converted into gate-level netlist using standard cell. This step optimizes the design for area, power, and timing. After synthesis, we perform floor planning. In this stage, the overall layout structure is defined, including core area, input or output pin placement, and power distributing planning. Then comes placement, where all the standard cells are positioned within the layout in an optimized manner to minimize delay and congestion. Following this, clock tree synthesis or CTS is performed. This step ensures that clock signal is evenly distributed across the entire design, minimizing clock skew and ensuring synchronization. Next is routing, where all electrical connection between components are established using metal layers. This is critical step as it directly affects timing and signal integrity. After routing, multiple verification steps are performed, including timing analysis and physical verification. Now, let's look at the result achieved in this project. The timing analysis shows that the slack is greater than or equal to 0, which means the design meets all timing constraints and operates correctly within the required clock period. There is no setup or hold violation, ensuring that data is correctly captured and transferred without errors. From a physical design perspective, the design achieved the zero DRC violation, which means it satisfies all manufacturing design rules. The LBS tech is also passed, confirming that the physical layout perfectly matches the logical schematic. Additionally, all essential output files were successfully generated, including the GDSII file, which used for chip fabrication, the gate level netlist, the SDF file for turning back annotation, and the SPEF file for the parasitic extraction. These outputs indicate that the design is fully complete and ready for fabrication. So, overall, this project demonstrates a complete end-to-end ASIC design flow, starting from high-level RTL design to final physical layout. It highlights my understanding of digital design, physical design, timing analysis, and verification, along with hands-on experience using industrial standard tools. This project also shows the ability to bridge the theoretical concept with practical implementation, which is essential for VLSI engineering knowledge. With this, I conclude my presentation. Thank you.